69 being the second most common. I can make a guess for why that might be the case. Did you know that 69 is the first number where if you square it and then you cube it, those two values between them encounter the numbers or the digits 0 through 9 once and only once. Yeah, it's the first number with that property, which I assume is why that was the second most popular answer.
But it turns out that 3 Blue 1 Brown actually undersold 69's niceness, because not only is it the first such nice number, it's the only nice number in base 10. And we can confirm this with a simple exhaustive search of all the possibilities. We can see that 46's square and cube have only 9 digits, which is not enough, while hundreds actually has 12 digits. Interestingly, the square and cube roll over at the same time. And we can just see 69 is the only one that works. Or we could also have watched Mind Your Decisions video. Like, what are the odds? But instead of answering that question, we're actually going to calculate the expected quantity of nice numbers because it's easier, and we're lazy. So let's assume everything is pseudo-random, like the digits. And pseudo-randomness is a big assumption. There are lots of reasons in problems like this that the digits would not be pseudo-random. There'd be a bias toward or against nice numbers. But let's just quickly for now assume that there's no bias. Okay, so the expected quantity is just the number of candidates times the chance that a candidate works, right? And the number of candidates is the number of numbers whose cube has the correct length, which we saw in base 10 goes from 47 to 99, so there's 53 candidates. And the niceness probability is the chance that for all the possible strings of 10 digits, the amount of nice strings divided by all strings. And the number of nice strings is 10 factorial, because that's the number of ways to arrange 10 digits. And the number of all strings is 10 to the 10, because that reflects the fact that there's 10 choices for each digit. Cool, so if we calculate, that's like 53 times 1 over 2756. So that's like the chance that 69 is nice, is 1 over 2756. But there's actually 53 numbers. And so the expectation is only 0.02. But yet there actually is one. So I did a computer search, and this represents the number of nice numbers in all of these bases. As you can see, there's one in base 10, and no other ones. This is where the computer got too slow. So it looks like 69 is pretty unique. So if you're like me at this point, you would conjecture that there are no other nice numbers, probably. 69 is actually unique, which is pretty incredible. But I did some complicated math, which I will explain over the course of this video, that shows the number of nice numbers you would expect. And as you can see, it's pretty low for 10, although it's actually a bit higher because there's a correction factor that I'll explain later. But as you can see, the probability is getting pretty low, so it's sort of supporting our conjecture. But then suddenly there's a ton of nice numbers. Once you get past, like, base 10, 109, 114, 118, suddenly they're abundant. So what's going on? And so for the rest of this slideshow, I will take you on a journey, an endeavor, if you will, to answer this question. Is 69 unique? As we search for nice numbers. So here's what's going to happen. So first there was like the cold open and like the plan, which you've like already watched now. And then we're going to look at some dumb examples of nice numbers and some cool examples of like almost nice numbers. And then like I made this claim with the graph and all like the points, but like how did I get those? Like that's probably a question you're asking yourself. And then like we consider the search problem of nice numbers more and like discuss the single good optimization for this search problem, but it's not good enough. So that's the plan of the video. So I dropped this blog post about the topic, and it got a bit of traction. And I also made this sort of fake money like betting market on Manifold about nice numbers and whether more would be discovered, and it was actually very fruitful. I I sort of assumed when I published the blog post that someone would tell me why this problem was actually like trivial and uninteresting. And sort of betters at the beginning did assign like a fairly high probability of learning of a nice number, like 69%. But then, pretty soon no insights were found and the market dropped to 26%. But what is this NA, you may ask? Well, there was this problem, which I didn't know what to do about this because I wrote the definition kind of sloppily. And it turns out this is also sort of a nice number. So I sort of, resolving NA means you sort of return all the fake money bets. So I kind of did that. And then I made a new one, and then people had a lot of cool ideas and cool generalizations. Also, there's more dumb, more trivial examples like this. But it actually is an interesting question to ask whether there are other complex nice numbers. I have not looked into this, so maybe one of you will, if you're so inspired. But yeah, once we restrict it to positive numbers, it's fine. Yeah, I mean, once we restrict it to natural numbers, it's fine. Yeah, so there's other types of generalizations as well. So over on the Reddit, there was a post that got some traction and some really excellent suggestions here. And then someone linked a Mastodon, which also mentions a sequence of numbers where they contain each digit exactly twice. And so you can sort of go on with this. And you might notice that there's like a convergence of starting digits where they're, sort of approaching something. And the reason for this is actually not super interesting. It's just because these are abundant. Like this septuply nice number has a cube that is like one of the very first cubes that has this number of digits, that has the correct number of digits. So the honest truth is there's just a lot of quadruply and quintuply and sextuply and septuply nice numbers. Which together overall I'm calling multiply nice numbers, which I know is confusing because it looks like multiply. But they're, a little bit interesting. What's more interesting, in my opinion, is look at this. All you have to add is a leading 0, and then 5 is nice in base 6. Jan Miseli's beloved sexamal, aka the best base. But what's especially interesting about this is that not only is it the only nice number that's known with a leading 0, it's the only nice number that is just missing, almost nice number that's missing a single digit. And that digit happens to be a 0, and it happens to be at the beginning, so you can write it as a leading 0 like this, which I think is just delightful, personally. So there's also the quasi-nice numbers, where you look at other exponents. So cubes and fourth powers is a very natural thing to look at. And in fact, there's again only one, and it's in base 10. So all the haters that think base 10 is bad, it has the only nice number with squares and cubes that's known, and with cubes and fourth powers. None is known for like fourth and fifth powers, etc. First and second powers, there are a few small examples, base 6, 8, and 9, and also some more examples. And the quasi-nice numbers actually became invaluable later on because they allow us to test some of our hypotheses. And that sort of segues nicely into section 3. How did I get that graph? The formula for nice number ranges. And how do you derive that? So this is also getting to the sort of more technical parts of the slideshow. So have fun. So first of all, when my computer program spat out that 69 and base 10 was the only nice number, my first thought was that it was probably not working correctly, because I'm not that good at coding. So I had it print all the things that were off by 1. And I found a good number of those, so that gave me more confidence that it was calculating something correctly. And I also had to print the off by 2s. But the off by 2s created two mysteries. And the off by 1s collectively. Once I was sort of looking at them, there were sort of things I noticed that were just like notable. And I'm curious if you guys can predict them. So I'll quickly pause. All right, mystery number 1. These numbers are strictly increasing. Like in each base, once you go to the next base, you never have a smaller number. And in fact, there are these gaps in between. So what's going on with that? Also, why is there nothing that's 1 mod 5? Yeah, so luckily we can answer both of these questions. All right, so we got this slide. Let me talk you through it. So remember a long time ago, we noticed that 100 rolled over, like the square and cube both gained an extra digit at the same time. So there's no numbers in base 10 where the cube is exactly 11 digits. That will never happen. But it will also never happen at exactly 16 digits. Because that's like 1,000 squared and cubed. And in fact, we can generalize. So we consider some base that is 5k plus 1. Now b to the k in base b, well, again, b in base b is 1, 0. So b to the k is just 1 with k zeros. That's what 1 to the k zeros means. And when you square it, you just double the number of zeros. You get 1 to the 1, 0, 0, 0, 0 with 2k zeros. And cubing it gets 3k zeros. So we put them together, we get 2 1s and 2k plus 3k zeros, which is exactly 5k plus 2 total digits. But remember, b was 5k plus 1. So that's 1 over the number of digits we want. But if we look at these numbers, this is clearly the minimal number with 5k plus 2 digits. The minimal cube with 5k plus 2 digits. And if we go down to the number right below this, b to the k minus 1, we will expect to have 5k digits. And there's simply no way you can have anything with 5k plus 1 digits. In b equals 5k plus 1. So no base that is expressible like this, that is equal to 1 mod 5, can ever be nice. And it turns out later on we'll actually be able to eliminate a second modulo residue class. So that's something to be hyped for. And if you want, you can try to predict which one it is. But this is how we eliminate 1 mod 5. So we can use similar logic to think about the ranges for the other options mod 5. I'm not going to go too much into the nitty-gritty because I personally don't find it very interesting. But these formulas are valid for like the ranges of candidates for the nice numbers. And the basic idea is that when you have something like b to the 2k, where the base is going to an integer power, you increase the number of digits, right? Because you're getting to a 1 and some number of zeros. That's when the number of digits roll over. And so when you're going to a power that's b to the k plus 1/3, that means just the cubes roll over. Because b to the k plus 1/3 cubed is b to the 3k plus 1. And similarly with the plus 1/2 is when the squares roll over. And this just ends up being the ranges of digits that are valid. And how does this solve the mystery of strictly increasing? Well, we notice that these ranges are disjoint. And now it looks like they might almost be overlapping. But since b is slightly higher, the new b to the k plus 1/3 is actually a little bit bigger than the old b to the k plus 1/3. And so that actually perfectly explains this pattern we have where the numbers are increasing, but there's like holes in between. Like there's something between 583 and 936, or something between 2939 and 5333. Okay, cool. So now we understand that, hopefully. Honestly, I'm happy to wave my hands about all this stuff. The important thing is we have formulas. And so, for example, in base B, now that we know the number of candidates, and again, we know this niceness probability of pseudo-random, we can figure out the expected amount of nice numbers in base B. And so this is, for example, what it looks like in a base that is a multiple of 5. So here's the graph for multiples of 5. It looks, a lot like the graph you've already seen. Continuous. It's an estimate. And this is the estimate that I sort of publicized with this sort of tiny little spike, and then it's super low, and then it goes up at the end. But what causes this behavior of the function? Okay, so let's do some latexing, or latex as I like to call it to annoy people who know the correct pronunciation. So we have this expression. Let's see what we can do with it. First, we're just going to factor out this b to the b over 5 from this expression, transform it into this expression, totally valid, because of how exponents work. Then we have to deal with this pesky factorial. So we're going to use something called Stirling's approximation. And it does work well enough for our purposes, because you can see on our graph, when we add, the actual graph when you put in this function in Desmos is blue, but it sort of has this numbers too big for Desmos to handle issue. But you can see the red Stirling's approximation version is almost exactly the same, except it's a little bit different at the beginning. But over here in the middle, it's just like, takes so much zooming before you even reveal that they're slightly different. So it's pretty good. And what Stirling's approximation says is this formula for factorial in terms of more terms, but they're simpler terms. Okay, so let's substitute in Stirling's approximation over here. And the great thing is the b to the b terms cancel. So we're left with this expression. In order to simplify b to the b over 5 over e to the b, we write e to the b as e to the 5th to the b over 5, which is, that's what we're doing. And now we sort of have this. And now we consider this expression, we analyze it. This term over here, 1 minus b to the negative 1/3, doesn't matter. Because once b gets over 10 to the negative 1/3 is just so tiny that this is just 1, so we're multiplying by 1. And this actually has a natural interpretation, which is that when you're actually dealing with a number that's 50 digits, whether you say a number with 50 digits or a number with 50 digits or less is essentially the same. Because a number with less than 50 digits is just like a 50-digit number where the first digit is 0. But anyway, don't worry too much about that. So we have this term over here, which grows with the square root of b. But the key thing that drives the growth is this term right here, b over e to the 5th to the power b over 5. And this explains the root of the behavior, because e to the 5th is about 148. And when b is below 100, this is a number below 1 that we're raising to a high power. So it's going to make the overall answer very low. And sure, we're multiplying by the square root of b, so that helps a little bit. But once this number starts to crack 120, or especially once it cracks 148, you're raising this to a pretty high power. And this number approaches infinity. So this does suggest there's an infinite number of nice numbers out there, if only we could find them. Assuming pseudo-random. For the quasi-nice numbers come in handy. And again, recall the quasi-nice numbers are the ones that look like this, where the first power and the second power have all the digits. And these are the small examples. And we can use similar techniques to project the number of quasi-nice numbers. And in fact, if we do that, we get the purple estimates. Here 1 mod 3 is impossible for similar reasons to 1 mod 5. But when we actually calculate them, the nice thing about quasi-nice numbers, they're small enough that you can actually calculate the higher ones before the computer runs out. And it does show, look, there's a bunch of quasi-nice numbers. But they're totally off from our estimates, from this formula. So they're not pseudo-random. And look at this. Base 23, we expect 16, there's 0. Base 22, we expect 12, there's 28. So, maybe on average this is the right number. But what's going on? Now remember, computational efforts stopped around base 48. When I originally ran the code, I only got to base 30-ish. Base 48 represents, months of work, but it's exponential. So basically the situation is we need theoretical breakthroughs if we're trying to find the next real natural nice number besides 69. One thing that was often suggested was filtering based on the idea of last digits, which, it's a fairly straightforward concept. If you know the last digit of a number, you know the last digit of its square and its cube. So if those are the same, like for 6, for example, 6 squared is 36, 6 cubed is 216. And you can see how, for example, 76 squared, you know its last digit has to be 6 as well. Because, 76 squared is 10 times 7 plus 6 times 10 times 7 plus 6. And so there's these factors multiplied by 10, and the middle factor is also multiplied by 10. So anything that's 10 times some stuff, you can ignore for the purpose of the last digit. So when we really expand this out, we can see only the last digit is influencing the final result. Fun fact, by the way, 5776 is the only 4-digit number whose last 2 digits are its square root, by the way. That's only vaguely relevant. But the important thing is we can look at filtering by last digits to see which ones instantly fail. And then you don't need to check the whole thing for nice numbers. And we might expect this to remove an average of one last digit, since there are b digits in every base, and each digit naively has a 1b chance. So b times 1 over b equals 1. The reality is a bit better because 0 and 1 will always fail. In base 10, 0, 1, 5, and 6 all fail. So 40% of our search space is gone. But the problem is it quickly declines. As you get into higher and higher bases, it's removing a smaller and smaller and smaller proportion of the search space. Although, again, we do see the naive expected proportion is below the actual proportions. The actual proportion is doing better. And these are graphs generated by Joshua Brower, who also looks at filtering by more last digits. Because you can also imagine if you know the last 2 digits, you can figure out the last 2 digits of the square and cube. And so we get something, but frankly, the sad truth is all that matters is that these lines are not at the very top of the screen. Because we need orders of magnitude. We have an exponentially growing search space, so we need orders of magnitude levels of filtration. So we can do better. I think this just about says it all. No, actually, someone else suggested this, the manifold user Cat, and I was also baffled at first. Although I'm sure some of you with more number theoretic background are not baffled at all. But here's why it makes sense. In base 10, there's that classic divisibility trick for 9, where you add up the digits, and then you see their remainder mod 9, and then it's the same as the original numbers. Well, why does it work? The very core idea of why it works is that 1 and 10, or 1 and 1, 0 in any base, differ by b minus 1. And so the way this manifests itself is that when we are just filtering mod 9, so we don't care about any multiples of 9, again, we perform this factoring, and we see that the 10s separate out as 9 plus 1, so the 9s don't matter, but the 1 leaves us with the original number again. So we can see once we've done everything, we get 2 plus 5 plus 6 is the same as 256, mod 9. Incredible. But why exactly does that matter? Well, if we know a number is nice, we know all the digits in its cube. And if we get the sum of these, that's the triangular number of b minus 1. It's just 0 plus 1 plus 2 plus b minus 1. I personally like notating it with a triangle, but here I've done the conventional thing and notated it with a t. And if swapping digits doesn't affect residue class, or doesn't affect remainder mod b minus 1, we can definitively say that the sum of the square and cube will have the same remainder as this number, which is always the same for any base. Will always be the same for all nice numbers in a single base. And remember, the square and the cube, their residue only depends on the residue of the original number. Okay, you might not understand. I'm kind of saying possibly a lot of gibberish right now. So we're going to walk through an example. And again, bear with me. We're getting close to the end of the video. I just want to show this cool technique. All right, here I use the triangle symbol. The deadline, guys, it's in like 3 hours. Okay, so our target residue in base 10 is 0 plus 1 plus 2 plus dot dot plus 9, which is the triangular number of 9, which is 45, which is a multiple of 9. So it's 0, mod 9. And now we go through the numbers from 0 to 8. We square and cube them and we add them. And we look at their remainders mod 9. 0, 0, 0, 0 for 0, 3, 6, and 8. And these are 2, 3, 8, 6, and 5. So A number that has any remainder 1, 2, 4, 5, or 7 mod 9 that's not 0, 3, 6, or 8 can never be nice. But we also have a piece of evidence toward anything that's 0, 3, 6, or 8 mod 9 being nice. And by the way, 69, for those playing along at home, is equivalent to 6 mod 9. So, it works. That's the basic idea here. All you have to do is check mod 9 square and cube to see if it has the right sum. And because we know rearranging the digits doesn't matter, we know it has to be the same as this if it's supposed to be a nice number. Because a nice number's square and cube always have the same set of digits. That's the idea. And we can actually go through programmatically and generate a list of the legal residues for each base. So we can see 10 is an especially fertile base, as is 25. And there are some patterns here that we don't really have time to get into. But one thing that I do want to mention is that promised second residue class we get to eliminate. We get to eliminate all bases that are 3 mod 4 from niceness consideration. Now, how are we going to do that? Now, suppose that n is nice and b can be written as 4k plus 3. Now, n squared plus n cubed is b times b minus 1 over 2, because that's the formula for the triangular number of b minus 1. Just, you can check that if you want. Google it. I don't know. It's true. So if b equals 4k plus 3, we can substitute that, and you get 4k plus 3 times 4k plus 2 divided by 2, which is 4k plus 3 times 2k plus 1, which is an odd times an odd number, so that's odd. Mod b minus 1. And now also b minus 1 is even, so note that reducing mod b minus 1 does not change the parity of a number. That's important. Because any square plus a cube has to be even, because if an odd number squared is odd, and multiplied by another odd number, it's still odd. An even number squared is even, multiplied by an even number, it's still even. So odd plus odd or even plus even is always even. So the sum is even. And again, we're filtering by an even modulus. So it's both odd and even. So a base that's equal to 3 mod 4 can never have any nice numbers. Cool. So how much information is it when we know the residue class? How much does that help our search? Well, let's say we were trying to calculate 69 squared and 69 cubed. And we knew all the digits except 1. Now we could add up all the other digits mod 9. And we know what the residue class is supposed to be. It's supposed to be 0. And we know the last digit, if it adds up to 0, has to be 8. There's only one option, 8. And now sometimes if it's either 0 or 9, those could be interchangeable. But in the limit, this gives us about 1 digit's worth of information. And again, remember, since we're searching in bases like 100, 1 digit worth of information effectively cuts the search space by about 1 in 100. It eliminates over 99% of the possible niceness candidates. Or, in other words, if a number passes this test, it's 100 times more likely to be nice. So, cool. Now let's see our quasi-nice graph corrected for residue classes. So previously we just saw the black and the purple, and they were kind of atrociously off. But now, once we take into account the number of possible residue classes for each one, and remember 23, which we were mystified about, that's 3 mod 4. So it should not have any quasi-nice numbers, because this argument about 3 mod 4 also applies to quasi-nice numbers, if you think about it. And now our estimates, sure, there's some inaccuracy, but 10 versus 10.8, 25.8 versus 28, those are pretty close now, and there's errors in both directions, which makes me think this really is a good model. All right, now I'm not going to linger here too long, but this is a chart of the possible residues, and you can count how many there are, right? And so naturally I searched OEIS, the Online Encyclopedia of Integer Sequences, for these sequences of the number of residues at work, and I didn't find any. Although the sequence of residue counts, if we wanted 0 for all numbers, is, by the way. And I also checked the sequence of valid residues for quasi-nice numbers. Not there. but all terms except the first were even, so I tried dividing the entire sequence by 2. And that sequence is in the OAS as number of primitive Pythagorean triangles with leg n. And I'm pretty sure it's the same, which is kind of wild. If anyone wants to prove this, that'd be cool. Yes, I don't know, this is just a tangent. So, we got some orders of magnitude. This, very cool person, Wasabi Pesto, created this computational framework to do a search, tracking nice numbers, also by percentage of niceness, how close they are. You can see a lot of research here happened. A histogram of numbers by how nice they are. This sort of implies a pseudo-random distribution. But you can look at their search completeness chart, and you can see they've shown up to base 48. That's how I was able to put black dots through my data. Various people have contributed to the search, but you can see there's a long way away. Quite a long way away. Before we get to these higher bases, which aren't even more fertile. They just have sufficiently more numbers that they have a higher chance overall. Okay. So yeah, search. So here are some expected nice number counts that I generated using a spreadsheet. If we use residue class filtration, that knocks off a couple orders of magnitude. Up to base 65, recall we got it to base 48. There's 0.01 more we expect. And then, according to Ars Technica, the world's fastest supercomputer can perform 1.1 quintillion operations per second. I don't know very much about computer hardware, so let's pretend that one operation is enough to check a number for niceness. Then, on this supercomputer, it would take about 20 minutes to get a 1% chance by reaching base 65. What if we wanted a 3% chance? Then we'd have to go up to base 85. In our fantastical supercomputer one operation per number scenario, that would take 10 to the 13 seconds, or about 300,000 years. If we wanted a 10% chance, which was what the manifold market predicted at the time I wrote my second blog post, we would need to go all the way up to base 97, approximately. That'll be 10 to the 19 seconds. Among Wolfram Alpha's helpful comparisons is that 10 to the 19 seconds is the age of the sun times 69. Suffice to say that we'll need some more theoretical breakthroughs. And honestly, all the nicer for 69. It's not unique, but it's uniquely unique. It is part of a vast multitude of nice numbers, of which we can only know one. And isn't that so beautiful?